Alright, time for another draftphysics.com, debatephysics.com also. And I wish I could find somebody to debate with. Somebody reasonable, okay, who, isn't just going to play some, you're an idiot, or, that kind of crap, waste of time, and actually make arguments about the actual evidence that exists, the experiments that exist, and explain how one experiment's credible and some other experiment isn't credible and all that kind of crap. It'd be nice to be able to have a debate with somebody who could actually explain why there's absolutely zero evidence that it takes 25 times the fuel to spin something 5 times as fast. Anyway, that kind of stuff. So this is going to be a draft video talking about heat, which really is energy, and it's sort of always radiated as some sort of kind of a photon, you could argue. So it sort of ties a lot of subjects together. You could sort of argue that a beam of light is really a beam of heat, and if it's at a frequency we can see, okay, the higher frequencies. And frankly, in space, there's a whole bunch of this heat that we can't see, and that's sort of the subject. So I did a little bit of research, and it's, what was the temperature on Pluto? And you're saying, because it's pretty far from the sun, obviously it's not getting much radiation from the sun to heat it. And they had it at some number like minus 50 degrees Kelvin, or something around 220 degrees, 230 minus Celsius. And then I looked up the moon, and the coldest place on the moon, and they had that at 250. And so you're saying, well, how can the coldest place on the moon be colder than the coldest place on Pluto? So that didn't make much sense. And because they're relatively similar in size, it's hard to figure how one could be, how Pluto, much further away from the sun, could not have more radiation inside of it. So that didn't make much sense. But anyway, then the microwave background. So I asked how cold it is in empty space, and they say 2.1 degrees or something Kelvin. And I knew that's not true. So, I mean, it seems obvious that if the surface of Pluto facing empty space is minus 250, let's even say, then we're at, well, the 229 number is even more convenient because that gets us at 50 Kelvin. And that was my sort of guess, that in empty space it's warm. It's not, it's cold too. 230 degrees is very cold, but it's not minus 230 degrees Celsius is very cold. But obviously, in an absolute sense, it's warmer than 0 Kelvin, which is a lot colder. So anyway, so I was just thinking about how it relates to the whole draft argument, drag argument, in the sense that, there's two events. There's, my argument is that this force stuff is real, okay? It's a real pieces of it, a quantity of it, a quantum, right? A quantity of quantums, okay? And they all move the speed of light, and they all have the same momentum. And they're just bits. And so the bits can come at a frequency, and that means something to us, or it means something to our matter in terms of what color it's going to reflect, all that kind of stuff, what it's going to absorb and what it's going to reflect. So anyway, there's the two processes I sort of argue. One of them is the absorption, okay? So absorption means there was a free bit of stuff in the universe, okay? It was free. Okay, and absorption means it's not going to be free anymore. It's going to be pushing a piece of matter. So it's going to be going a lot less than the speed of light. So it was going the speed of light very fast. Now it's going very slow while it pushes matter. And it's occupied, let's just say. It's not doing anything else. It's just pushing the electron or the proton. And then the other reaction is, so when the object is actually moving, that means it has a force bit already attached to it, and it's moving this way, okay, and an opposing force hits, well, then you get this double reflection. So you get a reflection of the force back, and you get this reflecting. So now you went from one free bit to two free bits. Now there's two bits free, right? Both of these are free. This is free here, and this is a free one here, in a sense. And this one can, again, go forward, and hit something else and slow it down, but it's going to reflect, which means it'll re-speed this one up. So if there was one right behind this, you could sort of understand that, well, this one reflecting will end up slowing this one down, but the reflection will come back and speed this one back up. So it's essentially just transferring the slowness, right? So this one slowed down temporarily. This bit hit this one. Let's draw a following one here. It hits the one following, okay, and slows it down. But in that process, it released a bit that's now going to hit this one, right? The one that shot the bit at it. And now this one's going to go back to its faster speed. And so you really only keep now transferring through, this would be called conduction instead of radiant energy. Now you're conducting it because it's basically happening between electrons and not empty space. So this is your, so the argument is I'm trying to get to this idea of what creates a surface, and the fact that there has to be equilibrium at the surface, and with the ambient temperature, the 50-degree temperature is the one it has to match, so to speak. And if it doesn't match that, then it's going to be ejecting. That is, it's going to be do more decelerating, because decelerating creates that extra bit of force, and so it's going to excrete in the end more force. Okay, and so it has to lose force if it's warmer than the ambient space. So space is the only container for all these objects. It's the only thing that's forcing them to have a shape. They would just keep expanding logically, you could just argue, if it wasn't for something about space that's pressurizing, applying a pressure. And bent geodesic doesn't say much about that. Yeah, so I would argue it's obviously this photonic pressure. So there's a bunch of these infrared, microwave, all kinds of different radiation, and radiation that perhaps we can't see because we can't make a camera that can see it. See, in a sense, right, the idea is even infrared cameras work this way. They cool the chip so they can see the temperature, and the only way you can see it is you have to be colder than the temperature you're trying to view. It's something you're viewing has to be warmer than you are, and so it's pretty much impossible to make something colder than that really cold, and be able to make it into something that can actually detect anything. So, so making it really cold is hard, and then making it really cold and being able to make it into something that can actually look at something and see how warm it is another challenge. So anyway, the argument sort of is the thermometer can't go colder than the 50 degrees. Okay, so you can't see something colder. You can only see things warmer. Yeah, it's a simple argument. All right, anyway. So there's this transition where the force going in ends up equaling see, it can't equal the force coming out. Obviously, if the object is warmer, then more force is escaping, and that's why the object gets colder. So the argument is that it is the compression, the idea that you're putting more force in, accelerating things towards the center of something, okay, creating pressure, and all those are force bits occupied pushing matter, and therefore they're moving much slower than the speed of light, so they're stuck in here longer, all right, and so they're at a higher density when you're warming it up. And then when the thing is warmer than the external environment, the pressure pushing out is doing the same thing. So you're pushing more atoms out than are going in. And in the process of that, more electrons. And that process means that you're going to excrete more energy out, all right, because of the fact that the reflection freed 2 force bits, and under the right circumstance, that reflection will liberate that second bit in the opposite direction. It will slow down 2 bits. There's more to slow down, the more stuff moving out, the more interactions you can have with it, with the force coming in, I guess would be the argument. Alright, so this is a little too chaotic, so we'll try to sit there and restart this one. Yeah, it's complicated. Alright, so I'll try this from a different angle. So we'll even try a different color. Alright, so there's 2 states the force can be in. That is, it's free, okay, or it's pushing matter. And the argument would be is the more force pushing an electron or a proton, and at different speeds, depending on how much force it's collected. So if you only have a certain amount of matter, as you absorb more heat or energy, would mean that your motion is going to be at a higher velocity. And the argument sort of is the higher velocity will be represented by the scope of your oscillation. That is, how far you go in space before you go into more force. Okay, enough force to stop you and essentially reverse your direction. And you'll oscillate. So you could argue the stuff in the center of the Earth is stuck oscillating because the same thing that's happening this direction and wants to push it this way is the same thing happening in this direction wanting to push it that way. And so there's no such thing as it just standing still. It ends up having to move this way, encounter the force, get re-pushed back this way, and constantly be in motion. So how hot something is a reflection of how much force has been collected, stuck to matter, versus force free to escape. Yeah, so that's sort of what I'm trying to get to. And that, something that's warmer than the 50 degrees of the universe would have enough pressure or energy pushing out, stuff moving out, all right, to be in balance with that 50 degrees at least. And then if it's warmer than that 50 degrees, then it's going to end up converting this atoms that are atoms that are moving out are going to be more likely to cause the reflection. Okay, so you're guaranteeing the fact that you're going to reflect everything that comes in, but you're also going to give back more than just what came in. You're going to give back for more. You're going to slow more stuff down and cause more. So there is this idea, okay, that you really are liberating 2 pieces of force, and some percentage of that extra force that you liberated with a reflection is going to leak out. Okay, so that's sort of the argument. And so you're not just changing the frequency of the light. When the light hits, see, we live in this visual world, so I'm saying that you have to imagine that there's all this invisible energy that's part of what this event that's going to happen when the energy hits the surface. And the surface is really making the photon. The photon doesn't really exist till the surface makes it. So I could argue sort of from my previous other videos, you could understand, like in the slit experiment, the idea is that energy is going through, by both surfaces. And so this works for the single impediment also, obviously. And what's happening is that a portion of what will become the photon is actually being produced from one surface and the other surface. And that's what's making the frequency necessary to cause the effect in the material that will create the ejection of a photon, the reflection. So it's a whole mechanical process. The energy hits the surface, and if it hits it in the right pattern, then it will cause the reflection that you'll see. Yeah. Yeah. I guess it could be argued if something's at absolute zero, if something's very, very cold, it would absorb all the photons that hit it, so it could never reflect anything. Yeah, I think. Anyway, because the matter wouldn't be moving. None of the electrons could be moving against it. So if something is at absolute zero, there's no electron moving against a force. There's no capacity for there to be a reflection. There has to be an absorption. Now the fact that it can absorb and then through the electrical process re-emit the photon, that is, end up pushing the energy back out, because so sort of the argument is, you really have to do all these subjects at once in some respects. I mean, the idea is the atom has a shape, and when you put electricity through, you basically are changing that shape in the sense that you're pushing on electrons here, okay. Alright, you're pushing on the electrons here and here, let's say, and so these are the ones getting compressed, and as they get compressed, these get pushed out. And so the idea is you're moving an electron on the surface out, and you're doing it at a sequence. That is, you're doing it to this atom, then this atom, then this atom, and that's your polarization. So it's the size of the atoms that determine the frequency in some respects. It's how much compression you can put into the atom that'll decide how much time it takes for this event, and then the next event, and the next event, and that's your frequency. Alright, so it's sort of like the antenna, okay, radio antenna, in the sense that the electricity takes time to go up the antenna, and it's, that time that really determines, because each event's going to happen at a different time, and that's creating, again, the polarization of the light. And that's why the antennas are polarized, is because the electricity is polarizing it. The electricity is traveling in one direction. If you don't want polarization in one direction, well, yeah, then you have like light, where the electricity can go in any direction. It's not a conductor. So it has electricity go this way, and then a piece of electricity go that way anyway. And that's why the light is polarized in all directions, is because there's not one direction that it's traveling. Yeah, that sounds a little better. Yeah, so we'll see if I can tie these things together a little bit better still. Alright, back. So these videos do help me in the sense that I think of things making the video that I didn't think of, because I didn't go through this process of trying to explain something. So when you try to explain something, sometimes you fall on things that you didn't think of before. And so something I didn't think of before is what happens to an electron in space. And there's this idea of charge, okay, that I'm arguing is what's going to compel it to always go somewhere, because the universe basically just looks like a bunch of protons and electrons to the electron, right? There's a place where there's an electron, and there's a place where there's a proton, and somewhere in space, there's a place that looks red, and there's places that look blue, and it's just going to head for the place that looks the reddest, or it's going to head for, it's going to do something some kind of crooked line. It could start off this way and bend this way, that kind of thing, because there's more than one proton that it's attracted to. But anyway, the point is it's always going to find some place that's redder than blue, less blue and more red. So you can't really throw one without it, with anything around it, any kind of atmosphere, because it's going to be constantly being pushed towards, at least towards atoms. And so it could have enough velocity to miss the atom. It's heading in this direction. The atom's over here. It wants to get there, but it misses, and just has its path deflected. Or it can hit the atom, in the sense that it hits an electron. It'll move the electron. The electron on the other side will move. That's the pressure. You push on one electron, you push on the other two, you also push on the other one, you push on all of them. And, and that pushing is, they're in a universe of 50 degrees of a lot of stuff hitting them. And so they end up pushing into that force, which means you make a new element moving. Now, it might be moving at a, so it might be moving in a different direction. But it's still going to have the same, it's a photon, it's a piece of force moving. So you've changed the frequency anyway. You've made the field more dense. The reflected field is denser the more stuff that's going opposite the field that's coming in. Has to be. So it's the whole idea that everything's expanding. When it's hot, it's expanding, and there's something that stops the expansion. And that's the field that's getting reflected or compressed. So it came in this far apart, and it's going to leave, this far apart, that kind of thing. Anyway, but the thing I was thinking about electrons is they're also affected not only by this charge thing, but if there is a dense piece of matter that is a bunch of electrons and protons, the fact is the density of that matter is also creating gravity. So the very fact is that less force can actually get to the electron from this way, less force that's going to be opposing its direction. So it's going to be moving towards that because there's less absolute field for it to interact with. So it's not going to have the same issues of, the equality of drag will be disappeared because some of these bits of force won't exist. So some of the force that was going to be in its way, and so it would only maintain its velocity, keep the same velocity, is instead now it's going to have a faster velocity because less force is in its way. So gravity is also going to affect it. So it's not only going to be affected by charge, it's going to be affected by gravity. I don't know how much that matters, but it just has to do with it's this idea too that electrons, when something's charged, if I put a charge on this and I'm adding electrons and they're creating gravitational pressure, that is, it's like adding mass to the surface of the earth, it's creating more pressure inside the earth. There's no way around that. So I add more mass, I add more pressure. So the more electrons you put on something, the more pressure they're creating because they're a mass pushing towards the center also. And but that doesn't change its appearance. So somehow, you can put a lot of charge on something, meaning there's supposed to be this higher density of electrons, but it doesn't change the appearance. So there's something about the electrons being part of an atom that's really important to the appearance, which means the reflection of the photons actually. So the extra electrons are either too small a number, or they're not, they're too elastic. They're too free they're too, they don't create enough of an impact to the atom when they are hit by the force. So they end up just transferring it as conductive heat, motion. They end up just absorbing instead of, they're less likely to cause a reflection, I guess, would be the argument. So you can't see their existence because they don't reflect. They move in more, and they don't move back out. Something like that. Yeah, I have to think about that one some more. Alright, so one of the things I wanted to get to, and haven't gotten there yet, is whether heat should be understood as atoms moving, or really it should be understood as just electrons and protons moving, so that you could understand that if you did have an atom, a net positive nucleus, I guess I should draw that differently, net positive nucleus, has electrons in it. So again, it's made out of electrons and protons. Neutrons are an electron and a proton. So it's twice as many protons as electrons. And so it has a net positive. And the electrons are obviously out here. The rest of them are in places where the protons are providing, where they can see a proton. And the empty spaces are obviously where they could see an electron. So the electrons won't go where they can see an electron. They're going to go where they can see a proton. And obviously they can only get so close. And that's where the temperature thing comes in, because you can understand that the less they're being jiggled, that is, if the electrons are looking at a proton, the problem is that they can't move closer to each other, okay, into the vacuum that's between them. The vacuum created by the fact that all the blue energy turns to red energy that comes out of a proton, and any red energy goes in an electron and comes out blue, which means it's inert to a proton, so there's no pushing force between them. The blue one is excreting blue, and the red one excretes red, and those, red means nothing to a blue, and blue means nothing to a red. Anyway, and so it's all this motion in wrong directions. You can understand that's going to cause them to maintain some distance. They won't be able to get very close to each other because they keep changing their line of sight. And so they have to keep some distance. And so obviously the colder you make them, that is, the less they're jiggling, the tighter and tighter this relationship gets between the electrons and protons. They get closer and closer. All right, but anyway, so the argument is that any motion by the electrons counts as heat. So any jiggling they're doing inside of an atom is also heat. Okay, so it's not just about moving atoms, it's about all the electrons and protons moving. Now obviously when a whole atom moves, it means that each part of the atom had to collect extra force. So if you understood that each electron had to have the same amount of force pushing it in the same direction, they all have to have that force that they've acquired to move the whole atom. And that the balance is created between them because the force is also interacting between all these pieces elastically. So one of them can't move in an aberrant direction without affecting all the others and changing their positions. So it moves collectively, and so that represents heat, but it's all moving in one direction. So it's sort of my argument that it's all heat. Electricity is heat. Photons are heat. Everything is heat, in a sense. It's all motion, and motion in one direction we call something else, right? And motion scattered we call heat. So it's really just the difference between something creating force dissipated in more than one direction and something that creates energy that's all moving in the same direction. And that's, it's really it's all just about the motion of matter. And so when you're pushing matter, you've used energy of the universe, you're using it, and when you stop matter from moving, you liberate force. And so that's why things, when they're in space and they're hot, hotter than the 50 degrees of space, 50 degrees Kelvin, they radiate, all right, away their motion. The little bits are jiggling, but they're producing more out motion than in motion, and therefore they're releasing energy to space. Yeah, that's the only, I don't know how else to say, but they're releasing it in this, kind of complicated way that, I tried to explain, in the sense that one thing moves, and when it moves and reflects, it's causing motion, and that motion will end up being reflected back into this object, regaining its momentum, so that the next thing that hits it slows it down again. The same process takes place. So you're guaranteeing the reflection. I guess I still haven't been able to make the full argument for how. So you could argue, okay, that the energy comes in, okay, it's reflected out, and the part that goes this way, part of the energy that continues in this direction, and it does continue in this direction, goes right through the center eventually and comes out the other side. And so that's the extra heat that you radiate. So you not only radiate the force that came in, reflects, and a bit of force on the other side ends up leaving, because it finally gets through this whole process of going in this direction. So it finishes going in this direction eventually and comes out the other side. And so that's the extra radiation that you lose slowly to the environment. And it's kind of slow, right? So you take something hot and put it in empty space, it doesn't get cold instantly. It takes time for the process of dissipating the motion it has. The electrons have to keep making the exchange with the external field, and so there isn't enough density in the external field to take away the motion quickly. So it takes time for the motion inside the atoms to be converted into more force in the environment. Yeah, so that's something I'll have to deal with. It's another time issue where it takes time for the radiation that's on the inside to get to the outside. The radiation caught in the matter bits doesn't instantly radiate to the external field. See, doing this, say if an electron I push, but I'm not pushing on anything. I'm only pushing on 50 degrees. So I'm pushing on a very low density of force. And so that low density is harder to push on. It's hard to, I'm going to lose my momentum slower and over a greater amount of time, I guess is the argument. So I'm going to the electron will spend more time moving, the less dense the external field is that's pushing it the opposite way. Yeah, something like that is probably correct. All right, anyway, so this was, it's a draft video. No obligation to watch draft videos. Just largely because they're made for my own benefit, and mostly, and to see if it inspires anyone else, of course, to say anything relevant, which is very unlikely, but what the hell. So I mean, it's posted because I made it, so I might as well post it, but there's not much more reason to it, okay, because it's incomplete, let's just put it that way. The thought process has not been completed. So the only takeaway would be, I'd first argue that heat really should be understood as any electron or proton moving is an element of heat. Yeah. And because it's been accelerated. So the transfer of acceleration to an electron yeah, you made the external universe colder because you absorb force. Is the simple way to understand it, right? The absorption, that is, the force comes in, hits an electron, and moves it. Well, there's no reflection. So the external universe got colder because you took away a piece of force that was free, and now it's not free. It's pushing a piece of matter. So that simple argument that obviously this environment has less elements in it out here because you took one of them away. And, so when you're absorbing heat, you're colder than the environment. You're making the environment colder. Yeah. So acceleration makes whatever's doing the accelerating colder, as the thing that got accelerated is called hotter. But in some sense it's colder because the forces moving are now moving slower inside the object. So the object is hot in the sense that it has more force moving a slower speed, which is the interesting part. To be hot, it has to be moving matter. To be moving matter means you're moving force at a slower speed. But you've absorbed more force to do that, and that's the hot part. So, yeah, so it's a simple argument that it's more force. It's not just about frequency that decides heat. It's about density and how much force you're actually producing. So the sun's hot, not just because it's producing high frequency light. It's hot because it's producing a lot of photons, a lot of force bits it's releasing. And it's releasing them because it collected a lot from gravity. Yeah. It's it's collecting the 50 degrees, putting it in a tiny place in the center, very hot. All right, and then that has to, re-expand again. Yeah, I'm just trying to think of a way of saying it's not really burning anything. So because of its ginormous size, you could sort of understand that there's a huge surface that it's collecting the 50 degrees on, and that goes down into a tiny surface in the center. So you're taking all of that pressure that's on the surface, that's only 50 degrees, 50 pounds, let's say, and you're converting it to on a much smaller, tinier surface. So per square inch, it goes from being almost nothing to being, 5 million pounds. All right. So, yeah, I better quit while I'm ahead, sort of. Anyway, till the next time and such and so forth and whatnot. More work needs to be done. Yeah, drawings.